Okay, so now we're in this situation where instead of SC, we have a more relaxed model. Let's just say that's total store ordering. It's no longer trivial for programmers to analyze what an expected program outcome would be. It's no longer trivial. You can still do it. You got to be careful. Because we are already having this complexity, this difficulty. Another school of thought is, why don't we teach people to understand this better by getting rid of these intuitions that they held dear in sequential programs, that there is a thread ordering to statements, there is a global ordering, there are these transitive relationship of before and after event. Why don't we just tell them to get used to it, that if you write a whole bunch of statements, they don't necessarily mean one has to follow the other in some order. Every order is possible. And if you want to have consequences or certain ordering, you put in these explicitly. So on the left-hand side, it's a quintessential example for that. It's proposed by some people, and it's called weak ordering. It's written up as a paper. Nobody actually implemented the particular design, although you can argue some, particularly alpha, the consistency model was very close to this. And it basically says this: you have these new mechanisms that you can use. These are called synchronization primitives. An instruction, some type of instruction. You put these instructions in between statements that you want to maintain ordering. So in this example over here, I put in two things. Now they will happen in 3 order: 1 before 3, before 5. But the load and stores within box 1, there's no ordering guarantee to start with, no matter how you write them up. So if you have one instruction in front of another, so what? It doesn't mean anything. All it says is all the load and stores will finish before we allow anything from 3, all load and stores in box 1 will finish before anything from box 3 will be allowed to start. So this is good. Now you, rather than think back from a sequential consistency model and see what new things can happen, you assume less and you put in barriers to give you more determinism. So that's weak ordering. And I forgot the timing, probably about the same time, some other folks at a different university proposed a slightly different concept. They're even more relaxed in the ordering. They recognize the fact that at some point you want to do a one-way synchronization. Okay, what that means is you're trying to make sure something happens. You're not trying to isolate them. So take the 1, 2, 3, 4, 5 that we used to have, and we can organize them in this particular way on the right-hand side. And I have 2 different ordering primitives. They're different. Okay, they're both synchronization instructions that the hardware will provide you to describe some sort of ordering that you want, but they come in 2 flavors. One called acquire, the other called release. Okay, so what's acquire? Acquire, just like the name suggests, I'm acquiring some right to some data. So what really I need is to make sure the access doesn't happen before I get the right, which is why 3 and 5, 3, 4, 5, but really 3 and 5, the load and stores, I want to make sure that they do not happen before the acquire primitive finishes execution. Okay, What I am not concerned about is finishing whatever is in box 1 before moving on. Okay, so that's the difference between the left-hand side, the weak ordering. Suppose I, instead of using the acquire, I use a sync, right? Then I have to make sure all the things in 1 are finished before I'm allowed to finish this sync operation. But now I put in a different sync. It's called an acquire sync, if you wish. It's called an acquire. So when the system sees acquire, it says, okay, now I can start to do this, do the sync. Before the sync finishes, I cannot do anything in boxes 3 and 5. But I'm in no hurry to finish box 1. I can let box 1 start to, I can still allow box 1 to continue. So what if I do want to make sure that it's finished? Well, then that's the second type of synchronization. It's called release. Release is the opposite. It says, I am giving some permission to other processors. So I'm releasing this write. So before release is allowed to go ahead, anything before that has to finish. In this case, box 1 and 3. So you see these ordering arrows. They mean they have to finish before release can finish. If I'm releasing something and they're not finished, you know, some operation, let's say a load in here, call that L1, it's still pending, it's still going out. And there's a store here in box 1, let's call that S1, it's still pending. That's okay. That doesn't mean I cannot start to execute something in box 5 already. I can. Okay, I can start to execute something in box 5 because 4 is release, and it's not about whether I can execute anything after the release. So that gives you this one-sided barrier. An acquire makes sure nothing from below it can start to happen. A release makes sure nothing from before it is still pending before release is done. So let's take a look at perhaps the reason why this is done. You still remember this example? It's a typical consumer producer relationship. I have a whole bunch of code. I have a whole bunch of update data. Then I'm setting a flag. On the other hand, I'm spinning on the flag before I'm going out to read those data. And in this case, the two flag variables are slightly different in style. So the on the left hand side, the blue one is a release style synchronization. So I label this particular operation a release operation. When I do that, and as you can see, release flag equal ready will not even start until all the memory operations before that have finished execution. But if I have a load instruction, you know, I'm reading from, let's say, data 3 down here for P1, the system will allow that to happen. It doesn't matter. It's not related to this one-sided synchronization. This is about anything before it cannot be still pending. When they're all done, flag equal ready, that operation is allowed to move forward. Conversely, on the right-hand side, the flag equal ready is an acquire style. So if I have this, when I start to execute this instruction, I see, oh, it's an acquire style operation. So I can start to do it now, despite the fact that maybe I have a write to data 0 equals something in front of it, still going on. Okay. I can allow that to happen because acquire is not about finishing up your business, it's about preventing future accesses. These accesses, they cannot even start until my flag equal ready is completely done. Okay. So how do you implement these in reality? These synchronizations, acquires, and release, how do you do that? Well, the most common way processors provide these are what's called a memory barrier or memory fence instruction. Okay, in alpha, there's an instruction called memory barrier. In PowerPC, there's an instruction called sync. They can be used in a very simple way. A memory barrier in the instruction can simply say, okay, this is a barrier. Nothing from after the barrier can start before everything before the barrier is complete. That will give you somewhat like what the weak ordering is arguing for. A simple memory barrier, sync, doesn't differentiate. Sometimes they give you other flavors, they give you flexibilities. For instance, a write memory barrier would only enforce those constraints on writes. Reads can allow to continue. So if I have a write barrier, that means nothing before the nothing before the barrier. Nothing after the write barrier can proceed. No writes after the write barrier can proceed before all memory operations before that are done. Okay, they can give you that, but the most flexible way is what PowerPC gives you. The PowerPC has one instruction, but it gives you 4 bits. So the instruction may be, I don't know, the detail doesn't really matter, but you have your opcode somewhere, and then you have these 4 bits. Okay, so the opcode is, let's call that sync. The 4 bits you can give 0, 1, 1, 0. Okay. So there are 16 different operations. So what are these 4 bits? They're here. It's called the RR bit, the RW bit, the write to read bit, and the write to write bit. What does it mean? Okay, it's basically what to wait on the left hand side and what to block on the right hand side. So in this example that I have, let's assume this is RR, this is RR, this is RW, and so on. Okay, so what I have here means I have to block the RW bit is set. That means I have to block all the writes from after the sync operation until all the reads before the sync operations have finished. I also have to block all the read operations from after this sync the sync instruction. None of them can execute until all the write operations before the sync have completed. Okay, that's what it means. There are 16 different ways of specifying this. You can to have 16 completely different combinations. Okay, so for instance, if you set all of them to 0, this is not a sync at all. You're saying don't block anything. I don't need to wait for anything to finish. So this is obviously a useless combination. Or you can have an all 1. If you have all 1, that means stop any memory access from following the sync until all operations before that is done. So that's your most basic sync operation that we showed right here. So this is rather straightforward for implementation. From an implementation point of view, if you wish. Hardware designer, I can do this. It's very easy. I can count how many loads are pending, and if enough is pending, then I'm not issuing anything from below. But it's very hard to think about it and say what style I want. So this is really not solving the problem for the programmer, but rather pushing the problem to say, you know, I'm telling you how the hardware works, you go figure out what's the consequence. And one simple result might be, I don't know, I'm just going to use this because that's easy to understand. I'll put a sink over there. So in theory, the compiler is inserting these for you. In practice, I don't really know how well a compiler can do such jobs. So, okay, these are the models. People have been debating about them. This is really just what they are. And one final thing about all these reordering is the concept of right atomicity. As if this thing is not confusing already, there's one more concept called right atomicity. And we have to discuss them, because consistency is about these ordering, what can go before or after that, plus, or maybe I should say multiply whether a right is atomic or not. So what does that mean? What does atomic mean? Well, we've seen that. Remember this example where we were arguing about what should be the outcome. The quote intuitive outcome is for A to always print 1. But we showed you how in a system with slow propagation, right, that P1 manages to tell P2 about A is updating to 1 far sooner than it does to P3. So P3 doesn't know A has been updated to 1, but it knew B was updated to 1, and it follows out of the spin loop and prints a 0, or whatever is A before it becomes 1. So this is really the result of the right operation, A equal 1, this particular right operation not being atomic. Being atomic is just like the name suggests, it happens at a point in time. Before this time, it hasn't happened. Nobody thinks A is 1. After this point, it happened. Everybody thinks it's 1. So if that's the case, if it's atomic, P3 cannot possibly disagree with P2 about the value, and therefore A will be 1 when P3 exits its spin loop. Okay, so that's it. That's what right atomicity is. When we say it's natural to expect A to be 1, it's really assuming, oh, these statements are all atomic. It's either carried out or not carried out. Reading is sort of, by default, it's atomic. You go somewhere, you fetch the data. Okay, it's either this or that. At that point, your request is being served. That's the point your read happens. It always happens at, you can think about it as in a particular cycle. But write is not, because it needs to shoot down in our design. It needs to shoot down all the copies in the system. And it may not happen at one particular time. It may start at cycle 12 and the cycle 2580. So it's never really atomic. And again, what you have to do is to provide the illusion that it happened at a particular time. Okay, so this is not that a system is atomic or not. It's always non-atomic in reality, but we have to project the illusion that it can be reasoned as an atomic system, a right atomic system. Okay, so how do you do that? How do you provide right atomicity? The most straightforward enforcement, and I suspect what's always being done in the real world, is you collect all invalidation acknowledgements before anyone is allowed to read the new value. Okay, when you do that, you make sure that everybody's on the same page. I have a graphics to illustrate. So let's take a look at this. Here, I have a whole bunch of threads, I, J, K, T. These are threads, okay? And this is time. The y-axis, the vertical axis is time. As time goes by from top to bottom, certain things happen. So if I start to to write. It always consists of one node issuing a write, and we have to send invalidation, and they arrive at different nodes at different time. Okay, and if I don't do anything about this, I simply allow you. So I invalidate you at, let's say I invalidate node I at this particular time, and then after some while, node I or thread I executing on that node issues a request, there's a miss, it comes back to me, I give you the new value. So this is what's shown here in the dotted line over there. Okay, so I have the old version, new version. And if I allow every thread to do whatever the heck they are pleased, then I'm going to have old version happening, the old version for one thread is here, and the new version happens there, and so on and so forth. So if I take a particular time point, I see I have some old version. For K, it's still solid line. For T, it's some other line, and therefore it's a new version. So within this time period, if we allow what's called early read, basically any node can read the value, then you give yourself this problem. And the simple solution is to prevent anybody from reading. And it's by denying a read request. So while I'm invalidating this node all this time, I'm not giving anybody the new data. Only when I received guarantee that everybody has gotten rid of their old copy will I allow anybody to read. So then I don't have a consistency problem. Okay? I have some angry or impatient processors. All these shaded area is maybe someone sending a request to me, and I'm saying, hold on. Okay, so they don't have a value. So now I'm patching this even. You either have an old value or you don't have a value of the weight. Therefore, you will never have two processors disagreeing on what the value is. You will have them disagreeing about whether you have the value. One node can have the value. At this point, K may still have the old value, whereas T, if you ask him what the value is, the load instruction will not return. You will not get a value at that cycle. You will only get the value at this cycle after the invalidation has all been done. Now you can see this is a sufficient solution. It absolutely guarantees that there is no disagreement on the value, but it's not a necessary condition. Okay, you can do better. You can try to optimize this, and that's really not the point. The point is this works, and pretty much all systems do this way. I'd be interested if you find an opposite example. So let's recap. This is we have all the problems. We've addressed all of the problems. Basically, it is this. We have some implicit assumptions, okay? Whether those are natural for anybody or this is really we just need to educate programmers not to have those assumptions, beside the point. But those are usually held assumptions that operations take place atomically. Okay? We know that they're not, but when we're reasoning about statement, that creeps up. And they happen in a particular order, and the order is the program order. And when you have these assumptions, you may look at a piece of parallel code, expect a certain outcome that is not provided by a machine. In a single processor, in a uniprocessor, because of out-of-order execution, we are already breaking this assumption. Things are not happening according to program order. But we maintain the illusion that they are. And this is covered in 201, 401 extensively. we have these buffers, queues, reorder them. It's relatively straightforward to do that when there is only one thread involved. Okay? When there are multiple threads involved, the order illusion is that much more complex to maintain. It's a sort of like if you just one guy started to lying, as long as he keeps a book and tell everybody the same thing, well, at least he's consistent. If you have multiple guys start to lie and each make up their own thing, it's very hard to maintain, oh, they're telling some form of a truth. Okay, so what is the solution to this problem? Well, it's really two solutions. One type is to actually implement a very strict implementation that it makes sure that these assumptions are still, the illusions of these assumptions are still there. But that's very expensive in terms of performance. So the other solution is to tell you, to fess up, to say, you know what, this is what's really happening. We're reordering these load and stores, so deal with it. Okay, so that's really the two assumptions. So as if this is not confusing enough, there's one more problem, and that's called right serialization, and that's what we're going to cover next. It's not about consistency. This is part of cache coherence, but it's really related, and so we'll have to discuss that.